Almost everyone is here. Okay, so welcome back everyone for the second lecture of the 3-lecture series of Gordana Todorov. So today she will talk more on picture groups for valid quivers and cubical structures of cluster morphism categories. Please go ahead, Gordana.
Okay, thank you. Well, thank you again. Thank you for giving me a chance to talk again. And thank you for people who came to the talk. Okay, so as you can see, the title is more on picture groups for valued quivers. And the reason is because Tomoki Nakanishi made some comments about it. And then there are some interesting things that I would like to point out how it is related to his comments. And but then the other part is cubical structures of cluster morphism categories. And of course, we already heard the generalized version of these cluster morphism categories by, the nice talks that we had by Bethany, Marsh and Aslak, Buan. And so it might sound actually as if I'm going a little bit backwards because they talked about the generalized tau cluster morphism categories, and I will be going back to the hereditary case, but I kind of want to give more of a background and kind of motivation why it was done that way. And it was the notion of these cubicals, cubical structures, which was actually essential. So I want to kind of discuss more about that. So now let me start first about the pictures and picture groups. Okay, so this first part is just a recall. So picture, it just means it's a subcomplex of a triangulation. It has orientation on simplices and orientation on those simplices. And then we had picture group, which was defined with generators and relations, and generators are on all k-1 simplices. And relations are given when you go around k-2 simplices, and you have here plus or minus, depending whether it's concave one way or the other way, or it depends on the orientation of the simplex sigma. And now I just want to point out, when we talk about so we talked about that picture that we want to actually look at. There are other pictures that we want to look at, but right now I'm talking about semi-invariant picture for valued quivers. So valuation on quivers just means that you have these FIs at each vertex, and you have DIs and DJs at each arrow, and you have the condition that the product of these two has to be the same as product of these two. And you have Euler matrix, where you use these DIJs if arrow goes this way, and then you have the bilinear form. And then you have d beta. Again, d beta are hyperplanes or parts of hyperplanes. So I'm just kind of repeating what was done before. The only thing is I'm pointing out this. And then from last time, okay, so here now I just want to talk about this, what happened last time. So last time I thought, okay, I'm going to illustrate one example. Maybe it's better if I do it, let me just do it this way. Yeah, so last time I said, okay, let me illustrate on a valued quiver. So I took this valued quiver, and here is the Ausländer-Reiten quiver with all the modules here and all the representations. Because it's a valued, I'm using, because it has two here, I'm using C and R, because C is extension 2. And then we got this picture. So this was the picture, just the way it was defined. And these are the domains, the betas. And then when you look at this vertex, which is this, where you read the relations, you get x1, x2, and you get x2, x3, x4, I think I labeled them. Let me see what I labeled them. X4, X5. Oh, so, okay, so that means that I labeled this one. I guess I didn't write here. Okay, so let me just put, so this was X1, this was X2, this was X2, X4, X5, and X1. So using that, right? Relation was x1, x2 is equal to x2, x4, x5, x1. And I pointed out that this is not the standard pentagon relation, right? But we have this relation which has 2 terms on the left side and 4 terms on the right side. And that is as far as I got. And then Tomoki pointed out that this, and he pointed out that this is the relation that he gives to this quiver, or at least to the quiver with 2 vertices, which is this. So comparing these two, you can see x1. So I just modified notation. Okay, so in my notation, this would mean that, but in Nakanishi's notation, it was this. It was x which corresponded to simple 1, x which corresponds to simple 2, module which has 1 copy of S1, 1 copy of S2. And so this was Nakanishi's notation of this relation in terms of composition factors, right? These are the composition factors. So this means it has 2 S1s and 1 S2. Now I'm just rewriting, from this line to this line, I'm just rewriting it in terms of dimension vectors, but now on the quiver B3, right? So this is S1, this is S2, this is S2, this is this module which has 1 S1, S2, and so on. But there's always this square which appears, and I'm keeping this square, and that's important. And then I'm again rewriting this in terms of modules. Okay, so finally, this formula is the same as this one on modules. And now what I want to point out that, okay, now I need to use the whole side like this. Okay, so this is here S1, and this is the module S1. This one, which is also squared, is this module L, and this is the module L. And this was again S1. So both modules which are squared here are the modules in this tau orbit on the Alexander-Rayton quiver. And this is the tau orbit of the modules which have endomorphism ring to be our smaller ring R. So S1 and L had endomorphism ring R, and then the other S2 and the other modules which appear here had endomorphism ring C. So the modules which had endomorphism ring R, which are in the orbit of P1, are ones which Nakanishi squared their corresponding values in the group. So that kind of looked interesting, but first I didn't really know why it should be like that. But then we looked at okay, so here's now the picture. Okay, so this is the same semi-invariant picture. Notice this is the semi-invariant picture. This is exactly the semi-invariant picture that we had with Igusa, or in our paper, which is called modulated semi-invariance. It's on archive. It's not published, but it is on archive. So it's called modulated semi-invariance. And in that paper, we kind of pointed out that there are 2 kinds of semi-invariants. So there was this one semi-invariant, which was corresponding to S1, and this one, which was corresponding to L, and this one, which was corresponding to I1. So I have in red the domains of the so let me just write now here. So this is, as I said, in the paper, modulated quivers, or modulated, I think we called it modulated semi-invariance or something. So red lines are the betas, the domains of semi-invariance of weight dim S1, dim L, dim I1, which are modules which all have endomorphism ring R. So at that point, and actually in the paper, we call them real semi-invariants. So we kind of had the distinction between these real semi-invariants and complex semi-invariants. And now it is exactly the real semi-invariants, which are the D betas, and which are when we associate elements of the group correspond to the elements of the group which Tomoki squared. Okay. So this was relation. So as I said, this is relation that was Tomoki Nakanishi's interpretation of our thing or correspondent. This is in terms of modules and explaining that it depends on the endomorphism ring of the corresponding module. This is in terms of semi-invariant picture, where the domains of the real semi-invariants are again ones which are here. But then again, there was another question. Well, here we have a group, right? And we have a relation. So how is that related to the pictures as I defined in the general setup, right? Here was our beginning of the pictures. That was the beginning of my lectures about the pictures. So I still wanted to have a picture for that. And here's, so here's Kiyoshi. And I have this picture. So if we take, this is now again picture in the sense of definition. It's a triangulation with, simplices, and we define GL to be all axes which correspond to lines, and we get relations going around the lines. So I labeled, so the picture is very similar to what we had before, but notice here now we take 2 copies of X1, and there are 2 copies of X12, so that this will now, and it is a picture in the definition sense picture, okay? So now with that picture, I have these 3 relations. I have this relation, and this relation. So I'm just writing them here. So X1, X2, X2, X1, X2, that's the pink relation, that's this one. Then the green relation is this one, which is this part. And then the blue relation is actually the same as the pink relation. So the blue relation is the same as this. So these are the relations, and I'm just writing them, and they correspond to the relations on the picture. And now when we take X1 squared and X2, and this is just rewriting it, and now I use pink relation and get this. And then associative law, so I get this. Then I use the blue relation and get this. And then again, associative law, I get this. And then I use the green relation, get this. And this is exactly what was, let me just now do it here. So this is exactly the relation that I'm trying to put it, okay, right? So this relation, which was Tomoki Nakanishi's relation, is obtained from the picture here using the 3, so this is the corresponding picture to that, and now it kind of all makes sense. And so the comment is just that, this is kind of 2 different interpretations. So we kind of played, Kiyoshi and I played with this after we got this, and it was interesting to notice that it is, the squares are here, that the squares are here with the red semi-invariants, and also that this is the picture. And then, of course, at this point, we have a question, can this be interpreted as a semi-invariant picture of something? Because this is, okay, so this is our semi-invariant picture. Now, this is a picture of the group which has this element, this relation, but can that also be some kind of semi-invariant picture? We don't know. I mean, we were just thinking about that, but didn't do anything. So this is kind of just three ways of looking at this, so that it really makes sense to have this x1 square in this sense and this sense. Okay, so that is what I wanted to add about modulated. So now modulated semi-invariants seem to be even more interesting to us. So we're looking back at the paper and it just seemed to be more interesting. Okay, so now, as I said, there are two topics. So that was my first topic for today. And now I want to go to my second topic. Yeah, if there are any other interesting comments, yeah, I would really like, and it's interesting to think about these groups now. So, you know, any comments would be really interesting to add here. Okay, now I want to go to the second part, which is motivation for cluster morphism category. And then, as I said at the beginning, it does look like I'm going backwards because we already had Bethany, Marsh, and Aslak talk about cluster tau morphism, tau tilting cluster morphism category. So they talk this in general, but what I want to talk about is really how the whole story started about this. So this is the quiver, and here's our picture, semi-invariant picture, and here's the picture group. So this was all that I already talked. And the remark, okay, so here are a few remarks. So first of all, pictures and picture groups are defined and studied more generally, right? So this is semi-invariant picture, but it can be done more generally. The second remark is that picture groups of the semi-invariant picture, so these ones that I'm talking about, are related to other important groups. So they're related to unipotent group, as I mentioned before. They're related, I mean, a lot of people study this cat0 group, so they're related to this cat0 group. So these semi-invariant pictures do appear in other studies of interesting groups, let me put it that way. And then the other thing is that picture groups of subsets of semi-invariant pictures seem to be interesting, and we want to study more of these. So these are just kind of three remarks that I'm talking here about semi-invariant pictures, but they are interesting subset. Their subgroups are interesting, and they are studied in more general case. So it's just kind of three generalizations. Okay. So what we wanted to do was we wanted to study homology of picture groups. So here are these picture groups associated to semi-invariant pictures. But then the point is that sometimes it is easier to study homology of a space which has the same homology, right? So that's what topologists like to do, right? Instead of study, you know, get the space and then study homology of the space. So picture space is such space. So we want to study homology of picture groups, but picture space is the space which allows us to study homology because they have the same homology. So now quick recall about picture space because I will be using it. Okay, so again, we have these triangulations of Sn-1. Then we do the dual cell decomposition, and then we squish certain things. We identify all 0 cells become just 1 cell, all 1 cells become these little loops, and then the rest. Now here, what I'm putting here, I'm not going to go through that because this is actually part of my previous lecture, but this is just illustration of the picture. This is the dual space, and this is the picture space after we squish all the points to one point and we get these loops, and then we take each one of these 2 cells and glue them along these lines here, and that's how we get a space. And then finally we have this D3 which we put in. So this just explains what is identified, and I wrote it carefully for that previous lecture, but I'm not going to talk about this now. So now the theorem is let Q be a quiver of finite Inkin type. So for now, I'm talking finite Inkin type. Then the picture space, this XQ, which is this one here, is a K pi 1 for that, meaning it has the same, for the picture group, meaning it has the same pi 1 and all the other higher homotopy groups are 0. And because it is K pi 1, homology of GL of this group is the same as homology of this space, and that's what I already talked before. So this is the point. Now I want to discuss this part, that picture space is K pi 1, because this is something that I always just mention, it's true, but I didn't discuss it. And the reason that we introduced the cluster morphism category, so the original motivation for cluster morphism category was to show that this is true, that XQ is K pi 1. So now I want to discuss this. XQ is K pi 1 for GLQ. So here's the outline of the proof. So it's really just the outline, and some parts I will discuss in details. So the outline is, first, we need to define cluster morphism category. And as I said, the general definition for tau tilting cluster morphism category was already defined, but I will recall the definition here because of the next step. Okay, next step is prove that this cluster morphism category is really cubical category. Okay? Notice this is still not K pi 1. It is just that it is cubical category. I will define cubical category. Then the next step is that if you have a category which is cubical and you take geometric realization of it, it will be, well, first of all, I'm sorry, my step 3 is that the geometric realization of this cubical category is actually our picture space. So we have cluster morphism category, we take geometric realization of it, and then what we get is the picture space, okay? Actually, it is homeomorphic to a picture space, and when I come towards the end of the talk, I will draw the picture of geometric realization, and I will draw the picture of this picture space, and you'll see that it's not obvious at all that this part. So I wrote here is, but it really should be is homeomorphic. Okay. And then, okay, so now we get that this geometric realization is homeomorphic to our picture space. And then Igusa showed that the geometric realization of a cubical category is again a cubical space, okay? So from a cubical category, we go to a cubical space, which is our picture space. So, and his theorem is really independently whether it's finite or infinite type. So it's in all types, but it is hereditary. This is still hereditary. Okay, actually all our work is hereditary. It's only Buan, Marsh, Hanson, and one more name, which I have later. These are the people who are now talking about the same things in more general setup. Okay, but we were talking only about hereditary. Okay, so once we get that this XQ is cubical space, this is not enough to say that it is K pi 1. This is not enough for XQ to be K pi 1. So one needs more work. Okay, so now I will be going through all of these steps later. Okay, so now here's the theorem. It's a Gromov theorem, which says that if you have a cubical space, which we now have, our XQ is cubical space, then it is, okay, so here's the term, X is locally cat zero. Everybody at Brandeis loves to talk about locally cat zero spaces, but it is locally cat zero if and only if there's this link flag condition. And this is actually the condition that we check in order to show that this is cat zero, and then cat zero will imply k pi 1. Okay, so anyway, Gromov's theorem talks about the cubical space when it is locally cat zero, and that it is locally cat zero if and only if it has this condition. Now, locally cat zero, let me just kind of point out what it means. It means that there exists a faithful functor to a group, some group, such that first morphisms of the factorization. So you talk about factorization. So you talk about first morphisms of factorization are determined by pairwise compatibility. Now, this part here is, you know, when we define cluster tilting object, we define that cluster tilting object is an object which has pairwise hom and x zeros, right? So our definition of cluster tilting objects are actually pairwise compatibilities. So the cat zero category is a category which has such a functor, and it has this, that these morphisms have property like that. So this is, I'm not going to go into details. I'm not going to do this in details, but I just want to point out here. And the last morphisms also have the same property, but we will show, yeah, this property we will show on the picture, on the cluster morphism category, okay? But then it says that that's equivalent to this link flag condition, which says that every subset of k points where every pair is connected. So notice again, everything is in terms of pairs of objects, forms a k simplex. And this essentially means that if you have 3 points, and if you have this simplex and this simplex and this simplex, you must have this, and similarly for 4 and so on. So this link flag condition is essentially this condition which one checks, you know, so often one checks this property. Okay, of course, you know, then after that you go to the higher dimensions. Okay, so anyway, the Gromov's theorem says that link flag condition is if and only if locally cat zero. And then we have the theorem which says if Q is of finite type, notice I'm writing A, B, C, D, E, F, G because it is modulated quiver. So it has all of the modulated things. Then the picture space that we're interested in satisfies this link flag condition. So this is what I'm saying. This is checked on the picture space of all quivers of finite type. So these are our A3s, but also B3s and so on. And then if Q is of finite type, again these, then the picture space is locally cat zero. So this is using Gromov's theorem, which says, okay, so we check first, it satisfies this, and then Gromov's theorem says it's locally cat zero. And then here's this general fact, which I guess among topologists, I think it's okay, which says that locally cat zero implies k pi 1. So now from that we have that if Q is a finite type, A through G, then the picture space, which we first showed is cubical space, and then Gromov's theorem says that if it has length flag condition, then it's locally cat zero, and then locally cat zero implies it's k pi 1. So we get that it is k pi 1. So this is the outline or how it is shown that it is k pi 1. And that is the reason that we introduce cluster morphism category and show that cluster morphism category is a cubical, that the picture space is a cubical space, and then show that it is like that. Okay, so now I want to go and kind of talk a little more about these cubical properties. Okay, so let me go here. So cluster, this is something which already Bethany and Aslak talked about. So I'm just kind of quickly going to repeat. Okay, so cluster morphism category, you have that the objects are wide subcategories, and then you have that the morphisms are partial cluster tilting objects. So if you have one wide subcategory, you have another wide subcategory. I'm using alpha sub x to denote this partial cluster tilting. So if x is partial cluster tilting object, so that means x, first of all, has to be in W1. It has to be partial cluster tilting object, and right perp of x, which is hom and x, has to be this W2. So I'm repeating which you already heard, okay? And now the only, as Aslak pointed out, actually it's both Bethany and Aslak pointed out, compositions are not all that obvious, right? Because what happens is you start with cluster tilting object like this, which goes from one y to another y. Then you take another cluster tilting object in the second one, and you get to the third y. So now if x plus y is partial cluster, this is partial cluster tilting, okay? So if x plus y is partial cluster tilting object in here, then the composition is really defined to be just sum of these two. However, if this is not partial cluster tilting, then we need to find something else, right? So we need to find the z such that this composition should be alpha or z, because the morphisms are only given with partial cluster tilting objects. Okay, so how does one find? So there's a I don't know, lemma proposition something. I think we call it proposition. Given x and y as above. So x is partial cluster tilting here, y is partial cluster tilting here. And now the question, the proposition says that there exists unique z, which will have the first part, it will have that x. But the second part, y, has to be changed. So y will not be exactly y, but there'll be this sigma y. And so that now x plus sigma of y is actually partial cluster tilting, but there are many of them. So you cannot take just any. So there exists unique z such that this is partial cluster tilting, and the difference of the dimensions of the y that we started with and the new sigma of y, the difference has to be in the span of the summand of x. So you have your x, you have the summand of x, and then when you modify your y by sigma y, you modify it only by the things which are in the, which have these dimensions of xi. So this is the proposition that there exists unique z. And now here is that I notice I did not define cubical category. I did not say why cluster tilting category is cluster morphism category is cubical category, but here is exactly the description of one of the cubes, and that's how one does for every cube. Okay, so here's my example, 1, 2, 3, and here's the wide, the little dots mean wide subcategories. So here's the mod lambda, which is a nice wide subcategory. In mod lambda, we have P1, P2, and P3 as our nice cluster tilting object. Now, P1 by itself is rigid, tau rigid, I mean, cluster rigid. Well, it's rigid, obviously. And then here we get P1 verb. So this is the first morphism. Then with P2, we get the second. Here's our W2. And with the third one, you get this one. And now with this P1, I can continue with I2 and get this. Now notice P1 and I2 are do not form cluster tilting objects. So I cannot take some of these, but it is equal to this part here, to P3 plus P1. So this is how it commutes. So you get this map here, which I didn't write. This is actually alpha of P1 plus P3. Okay, but I didn't put it so that we don't, so each diagonal is actually some of the cluster tilting, partial cluster tilting object. And similarly, you do this way, and you do this. Again, you can see S3 and, oh, here S3 and S1 already form partial cluster tilting. So actually they compute, so it's this same as this. Now S2 and S3 do not form partial cluster tilting, but I2 and S2 do form partial cluster tilting. So each of the morphism compositions, when they're not partial cluster tilting, they're equivalent also to this. And this is the cube. Now I want to point out several things about this cube. Okay, now, oh yeah, I should say, which I didn't say. Okay, well, first of all, P1, P2, P3 was our cluster tilting object P. So that was what we started with, cluster tilting. Factorizations, so alpha of P1, P2 plus P2 plus P2, 3, which is alpha T, is this, which is the same as this, which is the same as this, which is the same as this, and so on. So we have all of these factorizations. Notice that all of these factorization, this is one morphism in the cluster category, and these are various factorization of that morphism. Now, in the factorizations, we have first maps, which are these 3. So these are the first maps, and you formally define them really as the first maps. Okay, so there is a formal definition. They form cluster tilting object. And then the last maps, which are these 3, they form C vectors for the cluster tilting object here. So notice I started with cluster tilting object P1, P2, P3, and actually dim S1, S2, S3 are the C vectors of that one. And furthermore, sequences of maps are exceptional sequences. Okay, so any one of these sequences are exceptional sequences. Now in sign exceptional, we talk about sign exceptional sequences. So you can, because cluster, okay, no, okay, let me just go back. Here I did it for cluster tilting object, and I should write here. For each cluster tilting object, create such cube. So for each cluster tilting object, create such cube. So I just did one of them. Okay, now I want to define cubical category, and this will just be illustration of many of the things that I'm defining in cubical category. So cubical category C is, first of all, small category. Now, every morphism F in the cubical category has a rank which is either 0 or positive integer. And if F is composition, then the sum of rank, then the rank of the composition is sum of rank. So this is just straightforward here. This is rank 1, this is rank 2, this is rank 3. So just as many as this. Notice identity, and identity has rank 0 because of the compositions. So identity has to have rank 0. So that's why here rank can be 0 or larger than 0. Now, if rank of F is equal to n, then factorization category of F is isomorphic to the cube, I and cube as a category. So here was my F, right? This was my F. And factorization was exactly the cube that I drew here. So this picture is illustration of the step B. Now, factorization of F is just, you take all the factorizations. I mean, it's just straight as that. And cube as a category, you can view it as a product. There's several ways of looking at it. You can view it as a product of categories, where you take this little category and these morphisms and take product of categories. It's just the natural category that one can obtain. Okay. Now, so these are the first two parts of the cubical category. Then, so notice the reason it's called cubical is because all of these factorizations are cubes of various sizes. And then another thing is that forgetful functor takes this factorization category and you send it to your original category C, and you send factorization, you send this to Z object. And this is an embedding of category, so it just has to be nice. The next part is that, this is an important part, the first terms of F, which I just wrote as first terms in all factorizations. So you look at all factorizations and you take the first terms, which in our case was these three. They completely determine F. So if you know, so if your F, if you have the first terms of factorization, which is like having cluster tilting, partial cluster tilting object that you are starting with, it determines completely the map F. And similarly, last terms of F completely determine F. Okay, so this is the definition of cubical category. And I believe that from this example, you can kind of believe that this cluster morphism category is a nice cubical category. And the theorem is that cluster morphism category is cubical category. So we proved that, and that's the important part, okay? So far I just did the second step. So let me just go first. So first we define cluster morphism category, and this, okay, I didn't prove, but I kind of indicated that it is cubical category. Okay, so now the next step is to talk about geometric realization being the same as the picture space, right? So this is, I'm talking about geometric realization being picture space. So now let me go. So this is step 3. This is cubical category. Here's step 3. It's the geometric realization of the cluster morphism category is picture space. So let me just kind of quickly recall geometric, we're just using standard geometric realization, which means each object corresponds to a point, each morphism to a line segment, compositions, fill in triangles, right? So if you have a morphism like this and a morphism like this, and you have these objects, then if you have a composition here, then you have to fill in that. That's etc. Okay, so now I want to do this. Let me just see, it's 46. Okay. Okay, so I want to, I'm looking on example A2. So here's A2, here's our cluster category, and here are all our cluster tilting objects. We have P1, P2, P2S2, this one, and this one. So here's P1, P2, I call it A. And there are two, so this is alpha A, and there are these two factorizations. Either I can do P1 and then S2, or I can do P2 and then S1. Here is alpha E, which is for this one. And again, so I wrote for each one of these cluster tilting objects, I wrote their corresponding factorization categories. Okay, and now I want to point out here that, okay, so we have P1, P2 is cluster tilting object, and this is factorization of that one. But we also have that P1 and P2 shift is cluster tilting object. So we put negative to this alpha P2 because I'm taking here P2 shift. And in order to have this negative, one has to put this negative. So here we have another cube, well, 2 cubes. So here's a 2 cube, here's a 2 cube. So I have our 5 2 cubes. But notice there is a lot of things which are the same. So these are factorizations of all cluster tilting objects. And now we want to put them together. Okay, so let me just point out some of them. So here's my first cube, and here it is. I just put it here. Okay, then we have alpha 2 S2. So here's the second cube, which corresponds to alpha beta, and I put it right here because both of them have this alpha P2, so I just put them together. Then the next one is S2, S2 and negative P1, S2 and negative P1. Okay, I flipped it, but then this one goes here. And you can see I put all 5 of them here, and I put them on the maps that agree. Now you can also, so now let me see here. So here are all these 5 factorizations, and here are the maps, and here is our main wide subcategory, and here are other wide subcategories that you can see here. And then here's the 0 wide subcategory. You can also see that here we use S1, oops, and this is also S1, this is S2, this is S2, and P2 doesn't have anything. So now I'm talking about geometric realization. So what I have to do, I have to take for every object, I have to take a vertex, and I think all of you can see that, you know, having these two the same, right? This would correspond to the torus, starting torus, and having these two the same would be, well, having these two the same, I guess, is this beginning of the torus, and then these correspond to these two circles, and then you glue these two together, and you get a donut, torus, okay? And then there's this one here, which is not filled, and that's this open space. This is really, oops. Okay. Okay. This is really open space here. So the geometric realization of this is this torus with this is cut out. Okay. This is empty space here. Okay. So this is the geometric realization. Now, our theorem says that the geometric realization of the cluster morphism category. Oh, I shouldn't be doing this. Let me do this. Okay. Geometric realization of cluster morphism is the picture space. So now here I have my geometric realization, right? This is the geometric realization. Now I want to say that this is picture space. Now let me just talk about the picture space. Well, the picture space, you take the domains of semi-invariants, right? So you have semi-invariant picture, then you take the dual cells. So here are the dual cells. Now each of these 0 cells correspond to just one point. Then I go along the dual cells. So here's a dual cell, and these two will be the same dual cell because of the condition that their perpendicular categories are the same. So that means I will get only one loop for these two. And then these two again have the same perpendicular category. They're on the same D domain of semi-invariant. They will correspond to another loop. And the green one here doesn't have another part, so it is just this one, okay? So this is how you attach it. Now you have to attach a 2 cell. So to attach a 2 cell, what you do, you take your 2 cell and you go along the boundary. So I go along the boundary, I attach the 2 cell, then I go through the pink boundary, then I go against the blue boundary, then I go against, pink boundary, and then I go around to the green boundary. So this sort of, if you do it carefully, it looks like that. So it's a bubble which is actually squeezed here and squeezed here. And actually this line is identified with this line. So it's this kind of bubble which is here thick and then is squeezed here and identified here. So you do that, and furthermore, this part which is not a thick bubble, because I just went once around the loop, that we can view it here, but it's better to view it inside here. So the space, our picture space actually does look something like this. Okay, I didn't put right, these are. So first it's like this, but then it becomes these. Okay. And the theorem says, okay, so this is picture space for A2. This is geometric realization for the cluster morphism category of A2. This you can see, I think everybody can see this as a torus with this little hole in here. This is another way, this is the picture space, and this is a theorem. So it's, what I want to point out, even on the example of A2, it's not obvious. So this is really a theorem that, you know, geometric realization is really a picture space because I mean, it tried to see even on these two, okay? And let me see, I have 5 minutes more, is that correct?
Yes.
Okay, so now let me just go quickly. I mean, the rest I already talked about. So this is now, you know, this 3, which says geometric realization is the picture space. And then we have that picture space, that this geometric realization is cubical. Therefore, the picture space will be cubical. Then Gromov's theorem says, well, if we can check that it has link flag condition, then it will be cat 0. So we check first that it has link flag condition. Once it has link flag condition, then by Gromov's theorem, we know that it is locally, I keep forgetting word locally cat 0. Locally, it just means that the universal covering is really cat 0. Okay, so from this 5 and 6, we get that if Q is of finite type, then the picture space is locally cat 0. And then there's this general fact that locally cat 0 means k pi 1. So that is how we get that it is k pi 1. and k pi 1 was what we wanted to show in order to check the homology, right? So the remark is now for finite type quivers, we compute homology using picture space. That's okay. And then here comes the remark 2, and that is Eric Hanson. He showed that picture space for Nakayama algebras is k pi 1. So now at this point here, when I'm switching to my purple color, okay, I am talking about the more general, right? So up to here, well, actually up to here, this was still hereditary. Okay, so up to here, everything was hereditary. And now we talk about non-hereditary case. So now we have the general cluster morphism categories. Let me use this. So we have cluster morphism categories, which are using tau tilting theory. So it is using cluster exceptional sequences for tau tilting, tau. Okay, all these words put together, right? And this is really nicely developed by first starting with Buan Marsh, and then we have Borve. So first it was finite type, and then it was for infinite type for all. So this is now this theory of cluster morphism categories is beautifully developed in the general setup outside of hereditary. So my talk was only about hereditary. And so there are picture spaces, there are picture groups. So all this is here. And as I said, Eric used this for Nakayama algebras and shows that the space is k pi 1. But then the question is, in general, when is picture space k pi 1? When is picture space cat 0? Because notice cat 0 only implies k pi 1, but it's not, they're not equivalent statements. Okay. Then there is a theorem by Barnard, Emily Barnard and Hanson, that for pre-projective algebras, they checked that cat 0 is if and only if they have type A1, A2, and A3, I believe. I didn't check, but I believe it's these 3 algebras. And then the question is it possible to have k pi 1, even if it's not cat 0? Cat 0, okay. Okay, cat 0. So there are all these, so it's all open, so it's beautiful. I mean, you know, we're really happy that Buan and Marsh started, and now it's really expanding. Hanson, of course, is here, Borre is here, and that the whole generalization is being developed. And so there are all these questions now about the picture spaces and picture groups, and of course, being cat pi, k pi 1 being cat 0, and all the things that we kind of analyzed here on the hereditary. And I just want to point out that it's not trivial, as you can see, even on this very first page, you know, this cluster morphism category, realization of cluster morphism category, and this picture space, that they are homeomorphic. So, you know, there are a lot of things which are non-trivial in here. And I'm at thank you step. Thank you.
So first, let me ask the people in the room if they have questions. Wow.
So, can you hear me? Can you hear me?
I kind of hear, but don't hear. Okay, try. Yeah, let me hear. Let me try to hear.
I just wonder, what's the definition of pictures? If the type of the quiver or your algebra is infinite?
I'm sorry, can you, I heard like every second, third word.
So I wonder, what's the definition of picture?
You can define that, you define d betas. You see, the picture, you know, when we define semi-invariant picture, right, we use Euler product and define d betas, which were what used to be domains of semi-invariants, okay? Then if you use tau perpendicular to G vector, so you create also, I mean, the G pans, I guess, and then intersect with the sphere, and then you get a picture like, yeah, I think with Nathan reading always also draws the same picture. So these are the same pictures. So it's you create hyperplanes as perpendicular and then intersect with the sphere, and then you get a picture.
And what if you have infinitely many intersections?
Well, then the picture, you mean like in infinite case when things become, when you start to get many d betas?
Yes. Can we still talk about picture groups or?
Yeah, well, yes, talk about pictures. I think this is kind of interesting to see. So you talk about pictures, but then of course picture groups would be infinitely generated, because then you have infinitely many of these d betas which are appearing there. But then it's also the thing that is not clear to me is because, okay, in tame case at least there is this inescapable region. So if you take only the domains which are up to that point and not completely inside of inescapable region, then you are getting, so they're very, okay, so let me say in a short way. So you do have infinitely many d betas, right, and infinitely many lines. Now you can consider various subcategories, which is what I talked about last time too. So you consider various subcategories which give you various subsets of these betas, which give you various groups. And then one can study also what happens with these kind of finitely generated groups going towards the infinitely generated group. But yeah. So that's kind of semi-vague answer about that. But you know, there's a whole collection of finitely generated groups which are coming from all these naturally considered S's and naturally considered subsets of the picture of the picture. Yeah. Okay.
But instead, one can still talk about the morphism categories, even if your algebra is infinite.
Yeah, about about, you mean morphism categories?
Cluster. Okay.
Well, yeah, but then the problem is the factorizations. You know, if you get infinite factorization, then they're not. I don't feel comfortable about that. Okay, I think it is something that would be good to know. Okay, and kind of investigate, but I don't have really answers.
Thank you.
Are there more questions from people in the room? Let's see. What about people who are virtual? Are there? All right, it doesn't look like it. So let's thank Gordana one more time. And the last and third lecture will be at the same time on Wednesday next week. Thank you, Gordana.
Thank you. Thank you.
Thank you.
Thank you.